Okay. Kia ora koutou. Morena. Welcome to today's webinar, where NeSI's consultancy team will elaborate on how your research can benefit from their service. I'm Nisha. I'm a research communities advisor and training lead at NeSI, and I'll briefly take you through some housekeeping notes before we start. So please note that this webinar is being recorded, and do mute your microphones. This is just to ensure that there's no background noise or interruptions while the speakers present. And we have a QA doc to capture any comments or questions that that you might have during the course of the presentation, and we'll address those at the end of the session, just so we can get to everyone's concerns. And let me pop that link onto chat now, if I can see chat. Yes, so here's a link to the QA doc. Yes, so please feel free to use the chat function as well. One of us will keep an eye on that during the course of the presentation as well. So now I'll hand over to George to begin today's session. George, let me stop sharing my screen.
Thanks, Nisha. I will share mine. Kia ora. Ko George taku ingoa. I'm the Science Engagement Manager here at NeSI, and that means that I get to work with this pack of experts that you will get to know through this session, working to help researchers do better stuff on the system. And I get to introduce a little bit about NeSI already, NeSI as a whole. So I'll keep it short and sweet. So we have a purpose. What we are funded to do, our collaboration exists for us to grow the computational capability and skills of New Zealand researchers, Aotearoa's researchers. And we do that through a bunch of different approaches, I guess. And it is important to sort of call out that there's the capabilities of making sure you have access to these sorts of things, big computers, and that's kind of what lots of people think of us as. You know, we're lots of big computers, but actually that capability and skills side of it is absolutely core to us supporting you guys. So these are the computers at the High Performance Computing Facility, HPCF, at Greta Point, NIWA's location in Wellington. We have Mahuika, and Maui is the one on the far right, actually, that in the middle is where our storage is. And we've just recently added, we've doubled the capacity of Mahuika with a bunch more Milan nodes, and that's added just a single rack to the end of the one with that beautiful fiery image on the end. So technology moves on, space and energy requirements reduce, and compute power stays the same or grows. So always good for us to keep refreshing. The other thing to call out here is it's not just CPUs. There's a growing pool of GPUs in here. We won't dig into that too much today, but we will be scheduling a webinar shortly where we go through all the different GPU capabilities we've got on the platform at the moment. So watch this space. This is just to call out all those different services. So I've talked through the HPC or the compute. We also have data services, and what we think about there is things like Globus, where we have a process and a service to support transfer around both the country but also overseas. So that's an interesting one to look into. We do also work with different communities to work out how to support their research data needs. So one way is storage, but actually it's things like repositories, So, you know, look out for other webinars and material on that stuff. Training, NeSI's leads our training efforts in our training community. Lots happening there. And then consultancy as well. Definitely, it's last on the slide, but not least. So I think I get to hand over. Oh no, I won't hand over to Chris. So what I am responsible for is making sure people understand who can use this service. And I think essentially, if you're a New Zealand-based researcher, there will be a way for you to access the service. If you're a collaborating organisation, University of Auckland, NIWA, Manaki Whenua, or University of Otago, they already have entitlements. So you can reach out to us through our support desk to contact us and ask about a consultancy. If you have a merit project, it's just the same as the compute. There's free access. So once again, pop in a support ticket and ask for a consultancy and we'll get back to you. Same for postgrad projects on the system. The slightly more, not challenging, but you know, there's more conversations here is around subscriptions. So if you don't fall into any of these other categories, we can have set up a contract with your organization to enable access. So that's a paid mechanism. And there's I've popped a few names in here that have those contracts already in place to tap into if that's helpful, or we can talk to you about what that looks like. All right, over to you, Chris.
Thanks, George. Yeah, so I've got a few slides now to talk about the consultancy service, and then after that we have some case studies of projects we've actually worked on to give you an idea of the type of work we can do. So maybe we go to the next slide. Yeah, thanks, George. Yes, so NeSI has the consultancy service, which is mainly delivered by its team of research software engineers and data science engineers. So that would be Alex, Maxime, and me. And maybe before we go any further, we could just do some brief introductions. So maybe I'll go first. And so I'm Chris. I have a background in materials science, and I was working as a researcher in the UK before I moved here. And it just happened that I was doing lots of programming work in my job there. So then I joined NeSI as a research software engineer to carry on doing that working with research software, but working across different research domains. So that's my introduction. So maybe I'll hand over to you, Alex.
Yeah, so hi, my name is Alex, and I grew up in Europe. I studied in Australia and worked in the US. And just like Chris, I was doing research, but more and more computing over time. And I realized that there was a need for people who would straddle the both worlds. And so that's how I became a research software engineer as well.
Thanks, Alex.
Yeah.
Oh, sorry. Yeah, keep going, Alex, if you want.
Yeah, go ahead. Maybe Maxime now.
Yeah, I was going to hand over to Maxime. Yeah.
Kia ora, I'm Maxime Rio, and I'm a data science engineer at NeSI, and I used to work in Europe, in Switzerland and in UK with neuroscientists mostly, but then I happened to learn more and enjoy working on HPC, and I had the chance to join Aotearoa, New Zealand, and so far it's been a real pleasure to work with scientists from all over the country.
Thanks, Maxime. So maybe just to give a bit of an idea of the sort of projects we work on, it says here that typical projects last for maybe 3 or more months, and that corresponds to maybe 100 or more hours of work. So, I mean, the 100 hours isn't a restriction, so we can work on smaller projects and we can also work on bigger projects. We find that most projects tend to be in the 100 to 120 hours range because of a few different factors. One of those is that the codes we're working with are fairly complex, and the research problems are difficult, so it takes us a bit of time to get up to speed with what the researchers are actually doing. And if we have much less than 100 hours, it doesn't give us much time to actually make an improvement after we've got up to speed. The other side of that is that, as George was saying earlier, the institutions have entitlements to a certain number of consultancy hours per institution, maybe, and they want to spread that out among multiple researchers rather than just one user using the whole entitlement up. So that's where there's a bit of a trade-off in the hours, but we find that 100 to 120 hours or more of work is usually required for the consultancy projects. The projects themselves are treated as collaborations, so we work closely with the researchers during the project. So the expectation is that both parties are putting effort into the project, and we think that's going to give us a better result. And also at the end of the project, we think it's much more likely that the work's going to be used if the researcher was coming along on the journey with us and helping with the project and the work along the way. Because at the end of the project, we hand over and the researcher needs to take over. There is an application process for a consultancy project, and that usually starts with an initial Zoom meeting where we would just talk through the project objectives and work items and so on. And then we turn that into an application form, and we take that process forward. So we're really keen to have, are really happy to have discussions with anyone on Zoom about their project. Next slide, please, George. So this just gives us like a very high level view of some of the different types of work we can do. It's very broad. We can do most work to do with research software or data science engineering. If you're looking at the diagram, a lot of work we do is around performance improvement. So this is code optimization, with profiling and improving efficiency of codes and IO performance. We also look at parallelization, and that can be software parallelization using, say, MPI or OpenMP, or it could also be workflow parallelization. So at a higher level, you have lots of tasks that can be done in parallel, and we can help with making that take advantage of the resources on the cluster. Other things we can do software development, so we can actually design and develop software from scratch. We can do algorithmic improvements. We can translate code from interpreted languages to compiled languages to improve performance, and we can help with offloading to GPUs and so on. And we can do data science. We can help with data science projects. So this could involve doing exploratory data analysis, designing and fitting of predictive models, and also looking at making sure that the numerical performance of your machine learning pipelines is optimized to run on NeSI. So those are just some examples of projects types of work we can do, but we'll have some case studies later which go into more detail on a few of the recent projects we've worked on. Next slide, please, George. Oh yeah, and just one thing to say, what we think makes consultancy service successful or consultancy project successful. I think the key thing is that the researcher and NeSI skills have to complement each other. So we have computational skills, so we have a lot of experience in the computational side of things. The researcher is an expert in their domain, and I think projects work really well when we come together, and that gives us a better result than we would if either party was to try and work on a project by themselves. So really, the skills are really complementary. There is a requirement to be able to, just quickly finish that one. There is a requirement to be able to abstract a problem, because we're kind of talking different languages. Maybe we're coming from the computational side and the research is the expert in their domain, and we need to find a common language where we can communicate really well together to make the project successful. We have regular meetings just to make sure that we're working on the right things, and that the researcher gets to set the direction for the project. And I think, yeah, there needs to be good communication, so that we often have questions so that the researcher can answer promptly, and then maybe when the researcher is testing our changes, they might have questions first, and we can respond to them promptly. And so good communication is important. Yep. Okay, I think we could move on to the case studies now. So I think we've probably got like maybe 10 or so case studies where we can give some examples of projects we've worked on, just so people have an idea of the work we can do. So I think I'll hand over to you, Alex, first, maybe.
Yeah, sure. Thanks, Chris. Next slide, please. So this is to illustrate, the kind of scientific domains we worked with. And this is a recent consultancy that ended last year, but it's microscopic imagery. And really what's happening here is that the researchers are looking at cardiac tissues and trying to find out, how that relates to cardiac diseases. And one of the things that happen in this particular case is that because you get an imagery on the left-hand side, you're going to get a picture that is a little bit fuzzy. But if you know the optics, what the optics is actually doing to generate the image, that means if you know what the kernel is, then you can sharpen the image by doing some fast Fourier transform. Now that fast Fourier transform can be very, very costly because of the resolution of the images. And so what happened in this particular case is that the researcher approached us and they wanted to find out whether their solution was performing well. They had already optimized code, they were already using libraries and so forth. So it really looked like there wasn't really much space to further improve the solution. But then we realized that this was a problem that could fit very well on a GPU. And at the end of this project, the researcher was able to run 3.5 times more or treat or process 4 times more images per unit time, which of course was a huge productivity improvement. Next. So this is again in the domain of medicine. But very different problem, although it's also a cardiac problem, but this time it's a simulation. So we had a researcher who wrote a Python code which simulates the blood flow in the coronary arteries. And one of the big issues here is that people have stenosis, they have blockage in their heart. I mean, it's one of the leading causes of death in the developed world. And they go to a cardiologist, and they go to 6 or 7 cardiologists, and each one will actually suggest something which is slightly different, maybe create a little bridge somewhere else. And so there is no uniform answer to a very specific problem. And so the idea was, well, can we do some simulations, and can we find out, what would be the best placement for a graft? And that's what that research project was about. There were 2 aspects in that research. I mean, one was performance improvement, 55x in this particular case. And then the other one was also to have a 3D visualization of those arteries. So we wrote specific code to do the visualization, and this visualization was then embedded in a graphical user interface that could then be used by a surgeon to try out different scenarios. Thanks. Next. We had totally different domains. So this is climate simulation, and climate simulations can be very, very expensive, but they have a hierarchy of models of different complexity. And just like in many other areas of research, and you have the high-end models, but you also have some sort of a lower resolution, sort of simplified physics model. And we had a researcher who worked on a tropical circulation model, one of these simplified climate model that is applicable to the tropics. And what we did for that particular researcher was identify where the bottleneck of his calculation was. It turned out it was a matrix multiplication, something that is very, very simple. And then the next thing was how can we improve the performance? So we tried different strategies, and one was using the BLAST library, combined with MTL. I'm not going to go into the details, but the important point here is that we also wrote a build system for the researcher that would allow the researcher to quickly try out one or the other strategy to find out which one was actually working best for him. And so that's a research software engineering, but people don't think in terms of build system as being very important. But once we had that build system, then it was very easy to try out different compilers, switches, and other things. And finally, we extended the build system to also support GPUs as well as the code. And the winning strategy turned out to be about 70 times faster than the original strategy. So that makes a huge difference. Instead of taking more than an hour, it takes a minute to run. And that's, of course, exploiting our new GPUs that we acquired a year ago or so. So that's it, I think. Next. One more. So another project we currently working with those researchers as well. They are from NeSI, and they're doing hydrology simulations. They want to find out whether some rivers are going to flood or not. Something very relevant if you are living around Auckland in the northern part of the country in particular. But these models, they have a lot of switches and a lot of knobs to turn, and so they need calibration, in other words. So basically, you have to take a lot of data, you have to run a lot of simulation and try to adjust these knobs. Originally, the code was meant to run on a desktop, a Windows desktop, and we ported it to run on our HPC platform. And then we created a system that would allow the researchers to run hundreds of those simulations and do the calibration automatically. So, you know, without having to sort of stare at the screen, but submitting the jobs. And Chris mentioned that workflows, you know, becoming ubiquitous, but also quite important in many areas of research, because when you have to run embarrassingly parallel jobs, then when you have 10 or 20, you might be able to do that manually, but when you have hundreds, I mean, you have to organize things automatically in some sense, and that's what workflows do for you. Next. And now I'm handing over to Chris.
Oh yeah, thanks, Alex. Yes, this project was in a slightly different area. This is a genomics code for doing de novo assembly. The code was called Trinity, and this example is about workflows again, and also runtime tuning. So Trinity is actually quite a complex workflow. There are a few different phases. And initially, the first thing we did in this project was we did some profiling to try and understand the behavior of the Trinity code. And we found out there were two distinct computational phases. The initial phase, which is multi-threaded and it uses very high amounts of memory. And then it has a second phase, which is a very large number of smaller, like less memory requirement parallel jobs that can run independent of one another. But it does have very high I/O requirements, so quite different behavior. And the default behavior for Trinity is that it just runs everything on a single node. So it does support some parallelism, but the parallelism is just within one node, which was found not to be optimal. Next slide, please. So what we did, we looked into trying to change the way that Trinity runs the embarrassingly parallel step of the job, because it's not good for it to run all on one node. In the table there on the top line, actually, you can see that's the default behavior of Trinity. So if you run on a single node, this particular example we were running, it could take maybe 24 hours to run using 16 cores all on one node. But we actually explored using this tool called HPC Grid Runner, which is a workflow management system that can assist with taking a large number of embarrassingly parallel jobs and spreading them out across multiple nodes of the cluster instead of just within a single node. And the reason that's beneficial is because like I said before, is the I/O bandwidth is really important for this code. When you have, say, 16 threads running on the same node, all writing to the disk at the same time, they're competing with each other for a limited amount of I/O bandwidth. But if you spread that out across multiple nodes, you get the accumulated I/O bandwidth is much higher. And you can see there, like if you look down at the bottom line, we're running at 60 cores across multiple nodes. And it's running about 10 times faster, but it's using less than half the number of core hours. So they're getting the result quicker, but it's taking up less space on the machine. So there's more other people can get their jobs on instead, and they're getting charged less. So it was a really, really good win there by using this HPC Grid Runner tool to parallelize that workflow. Yep, I think that next slide, please. Okay, so Warren Wilding's project. This project was with Jiawei Zhang from Scion. And this one's really about software development and software sustainability, with also some performance improvement in there. And the background, the question the researchers are trying to work on is they're helping with stopping the spread of wilding conifers around the landscape in New Zealand. And in particular, the code they've developed is looking at, if you release some wilding conifer seeds at a certain location, where will they end up? And this can help with managing the spread. Some of the challenges they were facing, though, so that they developed this code. The developer was no longer working on the project anymore, and the way it had been developed was it wasn't using a standard Python package structure. So that meant that when new developers were trying to come in and get involved in the project, it was a bit difficult for them to figure out what to do or where to start, because it didn't have the standard structure. Also, when you want to run the code, it required a bit of knowledge of Python and programming knowledge, and to actually be able to run the code, which sort of limited the audience of who could actually use the code. And also, there were also some issues with how long it was taking to run the simulations. The initial development focused on getting the answer right, but it wasn't optimized at that point. So we spent a lot of time just doing software development work, like refactoring the code into a standard structure. So now it should be much easier for someone else to come in and start working on the code. And we added tests and we added continuous integration to make sure the tests are running whenever someone pushes changes to the code, so that we can have good confidence that the code's still working when we're developing it. We also worked a bit on the user interface to make it easier for people who aren't programmers to use the code, and we now have a GUI interface. And we actually packaged it up into an application that can be distributed around so we could send an executable to someone on a Windows machine and they can just run it without having to install anything. And finally, most of the work was spent on the software development, but we also did some performance improvement, and we used number and vectorization to optimize some key routines. And I think for one of the realistic test cases they were running, it was actually a real case. I think they were running in the Mount Hood region. Docker were doing some management of conifers in that region. And I think instead of taking 1 day to run the simulations, it took about 30 minutes. So they were able to run much more, get the results much quicker, and be able to inform the actual work on the ground. Okay, next slide, please. Oh, thanks. Yeah. Okay, the final one. So enhancing capabilities of autonomous space missions. This was work with Adam Evans at University of Auckland. And this was about parallelization, software parallelization. So Adam's working on generating a high-order guidance algorithm for landing on the asteroid Bennu. As part of his work, he has this thing called automatic domain splitting in his simulations. And just a high-level idea of what this is, it's about when they're solving their simulations, they have to recursively split a domain if it doesn't meet some tolerance, some error tolerance when they solve it the first time. They split it into 2 domains, and then they solve the 2 domains completely individually. They're not 2 isolated simulations. But you have the same thing. If either one of those doesn't meet some tolerance, they have to split those again. And so you can end up with, in some of their simulations, thousands of splits. And this means you have thousands of different cases that can be solved independently. So it's a really good candidate for parallelization. But the researchers, they'd written this code in C++, but they weren't coming from a code development background, and they weren't sure how to approach the parallelization. So that's where we came in to help them with that. And we used a technique called OpenMP to parallelize the ADS routine. For a simple test case, it was running maybe 8 times faster on 16 threads, but we expect it to be better for more realistic cases. And we also parallelize another bottleneck in their code, so they can get a good speed up even if they don't have much splitting in their simulations now. We introduced the CMake build system, so the code's now more portable, it's easy to build. But a big part of this project was also upskilling, because the researcher really wanted to be able to continue the development themselves. So we spent a lot of time with upskilling them on OpenMP and C++ programming, and they're now able to carry on the work themselves and keep developing that code. And I think I hand over to you, Maxime.
Thank you, Chris. So for this case study, the Rainfall ML, we helped a team of scientists from NeSI's who wanted to dip their toes into machine learning for weather forecasts. And in particular, they wanted to try machine learning models for downscaling, which means that you go from a coarse resolution prediction to a higher resolution prediction. And for this project, we helped them to set up a workflow to deal with the life cycle of their models, so they could try tests and compare many models and easily add new models and to the suite of models tested. And more precisely, what we did here, we designed and implemented a SnakeMake workflow, and you can see a visualization in the graph on the slide, which contains pre-processing of the data, model fitting, model prediction, scoring, and then summary figures. Next slide, thank you. And typically this will be a summary figure, and as part of this consultancy, the scientists got a full system where they can implement a new model, add it to the workflow, and one of the 2 main benefits in this case for the workflow, one of them is you distribute the workload on the HPC cluster. And the second one is it only reruns the new models and the task to aggregate the results. So it does not recompute everything which is already available. Next slide, please. The next consultancy we wanted to talk about is one which is an out of HPC consultancy. So this one did not rely on the high performance platform. So we help Matthew McDonald from the Mata Institute to develop an acquisition system for eye tracking. More precisely, his focus is on detecting concussion using an eye tracker. So what you can see on the images below is he has a wearable glasses with cameras that are pointing toward the eyes, and so recording the pupil, and cameras that are pointing in front so they can record what's displayed on the screen of a computer. And so in this project, we helped by developing a plugin for the software, the open source software he was using. And the plugin was meant to display some stimuli at precise timing and to record the stimuli on screen in a set of files. And then we also did the post-processing of this data to extract some meaningful features for him. Next slide, please. And it's typically one of the type of features he was looking for, which are saccades, which means that when your eye is looking in at a point in space and then suddenly jumping to another one, and that's one of the key movements that they want to track and measure. Next slide, please. And the last case study I wanted to highlight here is the help to port a model for a deep learning model on the HPC. So this was for Saiful Khan from the University of Otago, and he wanted to use a deep learning model to detect birds from aerial images. So what you can see on the right is an aerial image of Braided River in the South Island, and these are black-billed gulls. So Saif developed a model using Google Colab and a mask RCNN model. And what we did is we helped him to migrate his notebook on the NeSI platform, which accelerated a lot also the compute because he had access to much larger GPUs. And the other part of this consultancy consisted also in testing a competing toolbox, which is called Detectron 2 from Facebook, which offer many more possibilities in terms of models that you can try and tune for your use case. And a final thing we did in this consultancy was, this is what you see on the right is only a crop part of the full images, which actually is very large. And so we wrote a little code to make sure that he can do the detection of the full image together and count the number of birds in the colony. And on this note, I'll pass the mic back to Alex.
Thank you. Yeah, thanks. Hopefully, the list of case studies illustrates some of the areas where we worked. I think there are other areas where we were active. Statistics, in particular, we worked with a group at University of Otago a few years ago, and they've been developing R code, which we vectorized and accelerated. So. By no means should that be a comprehensive list. It's just some points of references. The main message here that we want to convey to you is that we love your research, whatever your research is, whether it is in medicine, whether genomics, whether it is counting birds or biology or physics or chemistry or whatever. I think we have a deep admiration for your research, and we want to do everything possible to help you. No project is too small or too large. If you think, oh well, maybe that doesn't deserve a consultancy, maybe it's too big and so forth. Well, we can have a talk and then we can see. What we have found in the past is sometimes unexpected outcomes. These consultancies are a little bit like research projects, except that they're much shorter, typically in terms of time scale. They don't last typically for 4 years, but they sometimes things come out and things that we had not anticipated. An example was the GPU acceleration or things like that we had no idea what we would be able to get out of. It's always a good thing to contact us and just talk to us. The third point that we want to make here is that good research software engineering practice is something that will help you and will help us. So if you're starting a new project, start thinking a little bit about how to make your project fair, findable, accessible, interoperable, and reusable, because that will make your project easier to collaborate with. It's going to be easier to work with other colleagues, and it's going to be easier to work with us. Everything that we going to do with you and that we promote, I mean, I think in principle should help you regardless whether you're going to work with us or not. We understand that, you know, you do your research and you're expert in your research. What we propose here is to take over sometimes a little bit the computing and the mundane aspect of your research, you know, everything that has to do with computing, so that you can focus more on your research. And finally, I would say that, yeah, just send an email to support@nesi.org.nz if you have an idea, if you want to work with us, because I think there is a good chance that you know, we can have a discussion and that this could actually lead to a consultancy. We're very open. Perhaps a final thing that I want to say is that in this group, we all feel privileged to work with you researchers because we're learning so much. I hope you're going to learn things from us as well, but it is really a two-way kind of collaboration. For NeSI, it's very important to understand, you know, how researchers actually using the computing facility so that we can better serve you in the future. We can buy the kit that you need, and we can help you where you need it most. And so it's a win-win situation. And I'm going to stop here for questions and answers. I think there was a question in the, you know, about merit applications and does it require to have a grant? So I understand that, yeah, it does. But do you want to add something to that, George?
Yeah, I think so for merit, someone's helpfully posted the actual specifics of it, but essentially if you have a New Zealand publicly sort of provided grant that you've gone through some kind of eligibility process through it, so things like Marsden's, Rutherford's, the Health Research Council funding, SIF funding, if you're in a Crown Research Institute, there's a bunch of them. If you have one of those, then you are merit eligible. But I'd also say if you're not sure, flick us an email at support or come off mute now and we can discuss it. You know, we can stop the recording at the end and discuss it, because it can be a bit complicated or feel a bit complicated, but yeah, that's the high level of it.
If anyone has any follow-up questions, please feel free to either note that down on the QA doc, the chat, or you can unmute and start discussing with us.
Maybe one area, yeah, that we could emphasize a little bit, and I think it was mentioned by Chris, but it's sort of the porting of code from R, for instance, to a compiled language, and yeah, so we have worked in the past, for instance, with technologies like RCPP as an example. I know people who work in statistics and so forth tend to use R, and that's an area that we were active.
There is another question here from Jessie, thank you, around do you need a well-defined project? Jessie's interested in upskilling to prepare for an upcoming piece of work, but not quite there yet, looking at perhaps a consultancy around a toy example. Are we up for it, or should we suggest that Jessie comes back later? Does one respond?
I think that's a really interesting question. I feel like maybe with a toy example, that would be enough for us to do some useful work together that would help you in the future. Part of me thinks I'm really keen for us to be involved early on in the project. We might be able to help get some of that good practice in there at the beginning and make sure things are on the right track, which could be really beneficial for you down the line, I think. I mean, maybe it's something that we would have, we could have like a separate Zoom meeting to go more into the details. And then we could come up with a plan after that, I guess. That would seem like a good, I don't know if anyone else has comments, but that would seem like a good approach there.
Yeah, I totally agree. I think let's talk about it and understand there might be a combination of things like training as well that we could point you at. Always happy to have it, you know, a Zoom call or whatever to get started on the thinking. And yeah, a plan of attack, which might have a consultancy somewhere in it and some training and some other stuff. Let's talk.
And the other thing that we can add is and I think Chris said something about it, you know, the importance of communication. In many cases, the consultancy ends up with some sort of a finished product. You know, something is running, you have a workflow, you know, you have a model that predicts a certain behavior. But we could also have consultancies that are about guiding you into the right direction. So where the outcome would be, you know, a set of choices, or it could be a document that describes, you know, all the possibilities that you could go down the line. So that's another possibility, and definitely also agree with the idea of introducing those good research software engineering practice early on in the project. So if we're able to sort of guide you into roughly the right direction, I think that could be very valuable.
Thank you, everyone. Do we have any further questions? Jesse says thanks. If you do have any more questions, please feel free to pop them into chat, the QA doc, or you can just unmute yourself. We'll give it a minute before moving on to the last slide. Okay. While we are waiting, I don't know if I could quickly find the right slide. Point to. Yes, I hope I'm sharing my screen. Yes, thank you so much to everyone for taking the time to join us in this webinar. Thank you to the speakers for putting together so much of information, so much of useful information that you can take back and think about. And do reach out to us if you have any sort of confusions, or if you're not really sure about whether or not the consultancy would be the best way to go. Do reach out anyway, and we can figure that out together. And please note that I will be sending out a post-event mail out with useful links that you can go through. So the first thing is to join our mailing list. That'll keep you posted on any training events, any newsletters, or any event announcements that we send out. Like Alex mentioned, do reach out to support@NeSI if you have any concerns, questions, or anything that you might remember after you finish up with this webinar today. Please note that we have weekly online office hours as well. So that's something that we run every Wednesday. We alternate between 9 a.m. to 10 a.m. sessions and 3 p.m. to 4 p.m. sessions. So I'll send out the link to that article as well. And we run them every Wednesday. So I'll send that out. Apart from that, I think I can say on behalf of all of us here from NeSI, thank you so much. And we can hang around for a few minutes if you have questions. Otherwise, feel free to drop off. Thank you.